So you're going to have to take e to a negative power to get something that's less than 1, that's between 1 and 0. You're going to have to take e to a negative power. Now there's no power, no matter how small, that you can take e to where it gives you 0. So this logarithm is just going to shoot off down like this. The logarithmic function just shoot off down like this. It's never going to touch the y-axis because there's no value, no exponent you could put in e that's ever going to give you 0. Now, in this direction, it's positive. Now, it goes off like this and increases at a decreasing rate forever. Now, the rate at which it increases is constantly decreasing. So it's increasing at a decreasing rate forever. But it is unbounded. It will forever increase. Now, to know this, you have to make an argument. It's the same argument, I believe it was Euclid used, for the idea that there's no largest number, no largest prime number or something. All right. Conceive a maximum value for the logarithm. Say the logarithm, the largest value that the log of x can possibly take. Say the largest value, logarithm of x has to be less than or equal to m. M is the maximal value. Nothing can be larger than that. Well, then that would be to say that e to the m, e to this maximal value, would be the largest possible exponential. That m would be the largest. That if you put in a larger value than m, you wouldn't get a larger exponential. However, we do know that if you were to say plug in m plus 1, you would get a larger value. So, by a process called proof by contradiction, okay, we know that e to the x just is unbounded. It gets larger and larger and larger. We know this. You can demonstrate this. It just continuously gets larger as x gets larger. So because we know this, we showed as a necessary condition that if the logarithmic function is bounded, then that necessarily means that the exponential function is bounded. But because we know the exponential function is unbounded, we know that necessarily the logarithmic function has to be unbounded as well, because otherwise it would lead to a contradiction. So the logarithmic function grows at a decreasing rate. It always grows at a slower and slower and slower rate, but it never reaches 0. Or the rate at which it grows never reaches 0, and it never reaches 0, or it never goes towards 0 in a way in which it's asymptotic. So it's forever increasing at a decreasing rate, but it is unbounded. It isn't bounded by a horizontal asymptote. So these are the properties of the logarithmic function. Now, the next thing I'd like to get into is the definition of a limit. What is a limit? Or no, not a limit, sorry. The definition of continuity. There is an actual formal definition of a limit, but I don't really think it's useful right now. In fact, I don't really think it... In general, to a physicist, it's really not very useful. It's very formal. It's the epsilon delta formation. You can look it up if you want to. It doesn't really say much more than I said here. I pretty much intuitively explain what it says. But if you're looking for proof proving the existence of a limit from a formal standpoint, then you use that formulation. And it has a little bit more power than the one that I showed you here. Essentially, you find a delta for any epsilon, and then you've just proven the limit. So if you want to be sure that you have a limit, it's useful. However, for a function of a single variable, it's not useful. For functions of multiple variables or for functions of a complex variable, then the epsilon delta formation can be useful. But right now, it's not. It'll just bog your mind down with more complexity than is necessary at this point. All right, now, I said continuity. I gave you kind of an informal, that it's not broken up at all, or that you can draw it without having to lift your pen. Okay. What continuity really means in terms of limits, f of x, a function f of x, is continuous at a point x equals a if and only if the limit as x approaches a of f of x exists and the limit as x approaches a of f of x is equal to f of a. Okay. For example, let's go back to that function that I had, x plus 1 times the quantity x minus 1 divided by x minus 1. Okay. This has a discontinuity at x equals 1. Because even though the limit exists, the function isn't defined there. So the function and the limit cannot have the same value. Now, if I were to redefine it and say that f of x equals x plus 1 times the quantity x minus 1 all over x minus 1, if x does not equal 1 and f of x equals 2, if x equals 1, then the function is no longer discontinuous and is exactly identical to f of x equals x plus 1, because I've just set f of 1 equal to the limit of f of x as x approaches 1. So I've just fulfilled the definition of continuity. Functions like this are said to have what is called a removable discontinuity. That means by substituting in, like if you look at this function, as I said before, it's just a straight line, 45-degree angle, where right at x equals 1, there's a little hole. Just right at that point. Essentially, this is called a removable discontinuity because by substituting in a single point, the continuity is gone, or the discontinuity is gone. So anytime you have something like this, where just by changing the value of the function at the point of discontinuity, just changing that one value, it goes away, then you have what's known as a removable discontinuity. There's two other kinds of discontinuity. They're both non-removable. You can't remove them this way. So remember, just before I erase this, it's that the limit of the function as you approach that point exists and the value of that limit is equal to the value of the function at that point. Then it's continuous at that point. Now, this is the removable discontinuity I just talked about. It's got a little point. By substituting that value in right there, so by changing the definition of the function just slightly, you can get rid of it. Okay. The second type of discontinuity is where you might have a function which goes like this, and then there's this little jump here, and then there's another jump here, and another jump here. There's all these little jumps. This type of discontinuity is the second case. This is one type of non-removable. You cannot remove this discontinuity because any point you substitute in here still doesn't remove the discontinuity. Any point you substitute in here doesn't remove it. Any point you substitute in here doesn't remove it. You can't remove it by substituting in points. It doesn't work. So this is one type of non-removable. The other type of non-removable discontinuity is this one. It's the kind exhibited by the function 1 over x at x equals 0. It's where you have this. Or you could have this. It's any time, it's called an infinite discontinuity. Things go off either like this, or like this, or like this,